So typically we could just simply call this as reference temperature, it does not have to be 298. And as an example I have written a couple of things here. One is the atomic hydrogen formation reaction. So we noted that H2 is like the reference element for H, and therefore half H2 giving H is the formation reaction for atomic hydrogen, and so the delta HF naught 298 for H. So you look at the notation here. So in fact you could improve on the notation by saying 298 comma script mi on the subscript there, where script mi refers to the species for which you are looking at the formation, standard heat of formation. So here for the formation reaction of atomic hydrogen we get a number that looks like this. But on the other hand, if you now look at the formation reaction for the high H2 molecule, the formation reaction as H2 gives H2, and obviously you are now having no change across this reaction. Therefore it makes sense for us to take the standard heat of formation as 0. In the last class, one of the questions that came about for a definition of a heat of reaction and more so for the formation reaction was, if you now take the initial state at a certain pressure and temperature, and then you now wait until you come back to the same pressure and temperature for the final state and look at the heat that has been removed or added to the system during this process. What about the expansion work? Okay, because we now keep the pressure constant, that means we could allow for the volume to change, and there will be a pressure work that the system does because of the volume change that is allowed. So what we have to recognize now is note that all heats are enthalpies. Okay, that means, and it is not for nothing that we chose a symbol H that would imply that the heat is an enthalpy, or the reason why H is associated, the symbol H is associated with enthalpy is, looking at it the other way, it's actually a heat. Okay, so this is to say all the heats that we are looking at are not internal energies but enthalpies. Okay, so these are enthalpies, that means that is they include the expansion work. Alright. So for example, if you now say suppose we now have a container and a piston and a weight W indicates constant pressure, right, and suppose initially we have a mixture of H2 and half mole of oxygen molecule, and suppose we now have a heat interaction across the system boundary, and finally we now have a different volume, right, at which you now get a H2O for the final. So here we have a T equals 298 K, P equals 1 bar, and here we have T equals 298 K, P equals 1 bar, right. So the convention that we use, the convention is so heat transfer is positive when into the vessel. So positive when into the vessel, right. So we now take Q to be positive. if it's going inside. And so for here here as in this example where we are taking a H2 and half O2 initially and then it becomes H2O, the heat is liberated, that is leaving the system, leaving the vessel, leaving out of the vessel, okay, and that is we'll also try to now make it like QP. QP refers to the subscript P here for the Q refers to the heat transfer at constant pressure, right. So that is QP equal to negative 240 kilojoules per mole, right. So when you are saying per mole, it's actually per mole of what is formed. So in this case it is 1 mole of atomic hydrogen that is formed incurring 217.999 kilojoules. Here we are looking at 1 mole of water that is formed liberating 240 kilojoules per mole, right. So this means negative means exothermic, right. Positive means endothermic, right. And so what's happening here is first law of thermodynamics applied to the system means that a delta E, which is the internal energy change, is equal to QP minus the work done. You could write it the other way, that is the heat is equal to delta E plus the work done, or delta E is equal to QP minus the work done, and this means E2 minus E1 is equal to QP minus P times, let us say V2 minus V1, or you can also now rearrange things. So you can say E2, take this PV2 to the left hand side, so it becomes a plus PV2, and then you have a minus of minus PV1, so you have a plus PV1 on the right hand side, which can be taken to the left hand side becomes, you now try to group it with E1 with a negative sign, that's equal to QP. So from here you can see that this is actually H2 minus H1 equal to QP, that's equal to the delta H. So this is actually for any heat of formation, or any heat of reaction, okay. So for whatever you mean by heat of reaction as defined with respect to having a constant pressure and temperature at which you start out and coming back to the same temperature and pressure in the end will basically give rise to this, because we now keep the pressure constant, right, and you get back to this thing. So effectively what it means is the heat that you are looking at is essentially an enthalpy, right. So that's what you are, or an enthalpy change in the reaction. In the case of heats of formation, you will find that you are looking at reference elements to start with, okay, which are assigned a 0 heat of formation. Therefore you can directly say the heat of formation of a what should I say, of any species is essentially its enthalpy, okay, because it's not really an enthalpy change anymore, because it's changing from 0 for the reference element, alright. Therefore you can simply say that all heats are enthalpies, right. Now in the case of a constant volume process, of course, in the case of a constant volume process, we will have E2 minus E1 equal to QV, which means we don't keep the pressure fixed, the pressure will vary but the volume will be fixed. Okay. So I will leave it to you to actually find out whether QV will always be greater than QP or not. Okay, that's something that you can try to find out for yourself, and we will also look at some puzzles in the end between QE and QP that I will try to point out if we get some time, but let's just continue at the moment. Okay, and the other point I wanted to make is constant typically most experiences or with constant pressure, right. Example, or let's say gas turbine, rockets, stoves, etc. Fairly different ones, like gas turbine and rocket may be like aerospace, but stoves is not necessarily aerospace. Furnaces also, all these things you typically have a constant pressure situation. In things like piston engines, the pressure keeps the pressure keeps varying, the volume keeps changing. Okay, so it's neither constant pressure not constant volume, but let's not bother about it at the moment. For many applications, constant pressure combustion is a good approximation. Okay, the other thing is so standard tables. Now standard tables such as what's called as the JANAF thermochemical tables, catalog or give simply, you can say simply give delta HF naught 298 for many species. In fact, this tells you why we need to actually have a standard heat of formation. Okay, so it's possible now, if you standardize the conditions at which you want to catalog or tabulate the heat of formation, then it's possible for you to actually have tables like the JANAF thermochemical tables, which will give this for many species. Okay, so these are available. So if you now look at the heat that is released, QP, as essentially a delta H, which is nothing but H2 minus H1, right, that's what we had here. Just coming back to that after these notes, so we now have this can be written as then sigma I equals 1 to n Ni double prime, let's say HF Mi at P2 comma T2 minus sigma I equals 1 to n Ni single prime HF Mi at P1 comma T1, which is to say you could now consider any process where we started out with certain pressure P1 and T1, doesn't have to be standard, okay, and you now go through the process of the reaction to get completed, and you now reach a different state P2 and T2, which has got nothing to do with the standard. Alright, if that is the case, then we note that we are not using the standard heat of formation here. Okay, we are saying whatever is the heat of formation of all the species that are involved in the reaction, taking care that if Ni double prime were 0, that means it is not really a product. Okay, I'm sorry, if Ni double prime were, yeah, that's correct, if Ni double prime were 0, then it is not a product. If Ni single prime were 0, then it is not a reactant, so that will take care of that. So we essentially can sum over all the heats of formation not the standard heat of formation but heats of formation at certain pressure and temperature, that is for the products, minus the heats of formation for the reactants. So effectively this is like for the products and this is for the reactants. I have changed notation a little bit here for you and I am going to explain this further on. We are now beginning to use small h, okay, particularly because this is associated with per unit mole and you multiply by the number of moles, okay. So in some sense you can now call this as a molar specific enthalpy, that means you are talking about it as a per unit mole, okay. Of course we have been talking about having this as per mole as well, okay, but this is the standard heat that we are looking at. This is not the standard heat of formation yet, okay. I don't know if this makes sense right away. If I now write it like this, I'm actually trying to do something a little bit circuitous, in the sense if I have a reaction that is going on, let us suppose that I have methane plus oxygen gives carbon dioxide and water, let us suppose that that is the reaction that we are looking at. Now we are looking at here the formation heat of formation of carbon dioxide and heat of formation of water. Here we are looking at heat of formation of methane and heat of formation of oxygen, okay. Now we know that the standard heat of formation of oxygen is 0 and the heat of the formation reaction for methane, for example, would be like carbon at solid form plus hydrogen gives you 2 hydrogen gives CH4. That is a reaction that we have to go through. For the heats of the formation reactions for carbon dioxide and water are like C plus O2 gives CO2 and H2 plus half O2 gives H2 and so on. Those are not the reactions that we are finally looking at, right. So we are finally looking at CH4 plus O2 gives CO2 plus H2O. So why did we actually have to get into formation enthalpies? So essentially what it means is we are beginning a hypothetical process in our minds while we are writing this, and I want you to sort of get to understand that, which is, let us suppose that you started out with some reactants. In this case, in this example it's hydrogen and oxygen, or the other example that I mentioned is methane and oxygen. What it means is, and then they are at some pressure and temperature, okay. So what we are really basically saying when you are including the heats of formation is we are now going through unbonding their bonds, okay. So CH4 we now want to actually impart some heat to the system to form C and H2, which are the formation constituents, that is the reference elements. O2 is a reference element already, okay, as far as the, and then we now have the reference elements. We now regroup the reference elements, so we now have C, H2 and O2, these are the reference elements with which you could now form your carbon dioxide and water. So it is sort of like you got the reactants, you now unpack them or just debond them and then get back the reference elements. That means you have exchanged some heat in this process, keep that as an account, okay, and then get the reference elements to form the products that you are looking for, alright, and you will now get some heat out. So minus the heat that is supplied is the net heat that you are going to get. So you are going through a hypothetical reaction in your mind through a reverse formation reaction for the reactants to form the reference elements, and then a set of formation reactions for the products to get some heat transaction in both these steps, okay, and then you are looking at the net heat transfer to get you this QP. This is as it is beginning to get you into some hypothetical reactions that are not happening at all, okay. Okay, the next step for us is, so here our HF, small HF mi, as I said, was specific molar enthalpy, at any P and T, okay. In this case it is P1 and T1, in this case it is P2 and T2. Okay. So here we can now write, HF Mi at a certain temperature, and note that I am basically writing it only as a function of temperature. Why? Because we are assuming ideal gases, okay, and because we are assuming an ideal gas which is thermally perfect, we expect that the enthalpy, the heat is now shown to be an enthalpy, and the enthalpy should be only a function of temperature. Okay, we can now write this as delta H of naught 298 of this species plus a HF Mi at T minus HF naught 298 Mi. If you do not like 298, you can replace this by Tref, any reference temperature that you want, but you should look for standard tables that give you these things at that temperature that you are looking at. It is sort of like, in this step it is not exactly algebraically adding and subtracting things. You would find that this is showing up in these two places, so it is sort of like am I adding something and subtracting something? In some sense yes, but there is a physical meaning associated with this. What we are then saying is this is the standard heat of formation, right, and then this is what is called as the sensible enthalpy. Let me write it in capital letters, sensible right, that is what is called the sensible enthalpy. So what is going on? Why are we talking about something called a sensible enthalpy? Is that because that is the one that makes sense, whereas the other one is nonsense? Any ideas? Yes. Yeah. So algebraically this is not going to make sense, so do not worry about it. Okay, so what you are essentially doing is we are splitting this into two parts. One is what is called as the standard heat of formation that we have been talking about all the time, okay, and then the next one is what we call as the sensible enthalpy. So I am going to explain to you what these two mean. So here we are writing it in this way primarily from a notation point of view. Okay, so you do not go ahead and start cancelling things from left hand side.
The standard heat of formation is equal to at standard temperature, the fourth term. The second term is equal to that last term.
Here?
Yeah.
No, then it can't be.
No,
this and this?
This and last term.
This and this?
Yeah. You are right.
You could say that. You could say that. Okay, you could say that because as I told you, this H is not necessarily, I mean this is supposed to be like a change, okay, that is why we have the delta, alright, but it is changed from 0. Okay, so this is like enthalpy of heat of formation of H minus heat of formation. So if you can apply this equation to the formation reaction itself, what will happen is this is the heat of formation of H minus heat of formation of H2, which is 0, right. Therefore the change is nothing but the value itself, because you are basically taking a value and subtracting 0 from there. Okay, so you can write it, so this is a good question because it also firms up the notation that we are using. So the change as well as the value are pretty much the same, okay, because if you take the value and subtract 0 from this for the reference elements heat of formation, you get the change. So it's essentially the same, okay. But what is more important for us from now on is not how we split this, it's about what they mean, okay. So you are now looking at this particular thing as one term called the sensible enthalpy, the other one is called the standard heat of formation, which we are now familiar with. The question is what is meant by the sensible enthalpy, right? So what is sensible about this enthalpy?
It increases the temperature of the products further.
Further?
Yeah.
Why further?
Because more enthalpy is needed.
Well, this any increase in enthalpy that the sensible enthalpy shows is solely because of a temperature rise, okay. Or in other words, when you now talk about enthalpy of a species, you can now say this species now has a basic enthalpy associated with it at standard conditions, okay. You can take the standard at whatever level you want, okay. Your P and standard pressure and temperature can be whatever it is, and then you say the standard heat of formation at this pressure and temperature is this. This is arbitrary. The assignment of the pressure, the standard pressure and temperature at which the standard heat of formation is measured, that choice is somewhat arbitrary, but at that conditions, or those conditions, you now have a standard heat of formation that refers to the energy that's contained in the bonds by itself. For it to simply remain in that particular molecular combination of atoms at that particular standard temperature and pressure, it needs some energy, okay. That is what this is. Any further change in the enthalpy of the species from there on is purely by a change in temperature, okay. So that means you now stick in a thermometer or a thermocouple or anything, and then you measure the temperature, you should be able to tell what the sensible enthalpy is. So in other words, this is a part of the enthalpy that can be sensed by a thermometer or a thermocouple. So since it is sensible by a temperature measuring instrument, we call this the sensible enthalpy. So many times when you pretty much recklessly write that the enthalpy is directly proportional to temperature, we are always talking about the sensible enthalpy, we are not talking about the heat of formation, but the heat of formation is hidden, okay. So when you are talking about non-reacting fluid mechanics, where you are not bothered about chemical reactions and so on, you are simply saying, delta H is equal to Cp delta T. That is because the change in enthalpy is solely coming out of only the change in temperature, and therefore you are essentially interested only in the sensible enthalpy, and you do not even bother about the formation enthalpy, because the formation enthalpy is there and the species is not going to change. You are not looking at any chemical reactions that will change the species, but here we are burdened with the situation where the species is going to change. It's going to get, if it is a reactant, it's going to get depleted, if it's a product, it's going to get produced, right. Therefore we have to now begin to pay attention to the energy of the species itself, because it just exists at a standard temperature and pressure, and that's by virtue of the bonds, and we arbitrarily assign the bonds that are present in like these diatomic molecules like H2 and so on to have zero energy. That's like a datum, relative to which a atomic species that does not have any bonds actually accrues some energy for it to be remaining in atomic state, because it is not naturally existing, therefore some energy must have been given to get it to that state, you see. So even a lack of bond in that sense actually has some energy associated with it, because of the reference element that we take to be what it is. So this is a very, very important concept here that we are looking at, where this could now be catalogued in these tables, and then we primarily look at only the change in temperature for the rest of the enthalpy change for any species, right. So we can express the sensible enthalpy as HFMI of T minus HF not, let's say T ref MI equal to integral T ref to T Cp mi of T dt. Okay, that comes from the definition of Cp. So Cp is a partial derivative of enthalpy with respect to temperature, and therefore if you want to get the enthalpy back, then so you can now think about this like a constant of integration if you're now trying to integrate Cp with respect to temperature. For a calorically perfect gas, you can write this further as HFMI of T minus HF naught T ref Mi as Cp Mi T minus T ref. Now I want you to note that for the first time we are recognizing that each and every species may have different Cp than the other, okay. So Cp is actually species specific. Keep this in mind, it's going to now haunt you through the rest of your lives if you're doing combustion for the rest of your lives, okay. Usually we are saying T ref is 298.15 K, so usually T ref 298.15 K if you want 2 decimal places accuracy on the temperature there. So therefore heat of a reaction, this is any reaction that we are now looking at. For example, let's say methane oxidation to carbon dioxide and water, you can get Cp equals delta H equals H2 minus H1 equal to sigma I equals 1 to n Ni double prime, open your curly brackets here and then write delta HF naught T ref Mi plus HF T2 minus HF naught T ref, right. Take that back a little bit, so you could write combinedly for this, for each species Mi minus sigma I equals 1 to n Ni single prime delta HF naught T ref plus HF T1 minus HF naught T ref for species Mi, right. So you can see that T2 and T1 are showing up explicitly when we had these things parenthetically there, okay. But what about P1 and P2? They don't show up, huh? You're looking at ideal gases where the enthalpies are only functions of temperature, therefore the sensible enthalpy depends on the temperature, alright. So you can explicitly see T2 and T1 show up here, okay. But what about pressures? Do we have to bother about them, or don't we have to bother about them? Keep bothering about whether we want to bother about them or not, okay. So we will just proceed to what we want to do, which is look at the adiabatic flame temperature. We are now ready to look at the adiabatic flame temperature. Right. So what do we understand by adiabatic flame temperature? Why is it called adiabatic? We still don't know why it's called flame temperature, or do we? So in the first class we said the flame is nothing but a reaction zone, and we are basically looking at any reaction which is happening to start with at P1 and T1 and ending at P2 and T2, and we know how to write an expression for the heat released in this reaction given the heats of formation, the standard heats of formation of the species and the sensible enthalpies of the species, which are supposed to be tabulated. So the tables will actually contain a left hand column of temperature starting from, let's say, 298.16 and then keep on going up to fairly high temperatures, maybe 4000 Kelvin, 3000 Kelvin or something like that, okay. And then for every row of temperature you will now get the sensible enthalpy for that species, right. So you have the sensible enthalpy as a function of temperature, or if you don't want to deal with sensible enthalpy you can deal with CPs, and the way you want to deal with a CP as a function of temperature, you can fit in polynomials and then do the integration, or if you want to assume a calorically perfect gas you can now consider a CP that's constant over the range of temperature that we are interested in, right. So you can do all these things. So if you are given the Ni double primes and the Ni single primes, okay, and the heat of formation, the standard heat of formation and the sensible enthalpies, you could in principle find out the QP. But what's the situation here? What are we looking for? What are we trying to find out? We are trying to find out the adiabatic flame temperature, okay. That means we don't know the temperature at which the products will be when the reactants have burned, you get the products, okay. And we want to actually find out what will be the temperature attained by the products when they have reacted from the reactants without losing heat to the surroundings at all. Therefore they get the maximum temperature possible, because if you lose some heat to the surroundings the products will attain less temperature, okay. So not losing heat to the surroundings is what we mean by adiabatic. So if you now have an adiabatic situation, then you get the maximum temperature that is in principle possible for the products to attain from the reactants, yeah. So what would we want to do in this equation? What do we know and what do we don't know? Yeah, previously given T2 and T1 and P1 and P2 and N1 double prime and N2 double prime, and you get the sensible enthalpy from the tables and the heats of formation from the tables, you could find QP. But here what's given and what's not given?
Ni prime is given, and Ni double prime P2, if you assume constant pressure, P2 is known, and T2 is unknown.
T2 is unknown. What else is given?
T1 is given.
Sorry?
CP is given, I think.
That's fine, that's been given even before.
We have to find T2, no? CP, T1 we know.
So we have to find T2 is the question, right? So previously we were given T2 and we could find QP.
Yes.
Here what do we do?
We have to find T2.
You have to find T2. So what about QP?
QP is taken from 0.
QP is taken as 0. So the starting point for us is to take QP is equal to 0. So adiabatic simply means QP equal to 0, right? That means H2 is equal to H1, right? And when we say H2 equal to H1, the implicit assumption is constant pressure, okay. So if somebody doesn't mention constant pressure and talks about adiabatic flame temperature, it's implicitly assumed that you're basically hearing about the constant pressure process, okay. So this refers to this. Unless you want to explicitly talk about constant volume adiabatic flame temperature, then you have to say so, okay, because without that we are simply going to be equating H2 to H1. If you want to look at constant volume adiabatic flame temperature, what do we want to see? We want to say QV is equal to 0. That means we have to be equating E2 to E1. All right. Here we are looking at QP is equal to 0. Therefore H2 is equal to H1, implicitly assuming constant pressure. So adiabatic flame temperature assumes a constant enthalpy and constant pressure. A constant enthalpy given by H2 is equal to H1, and the definitions of heats essentially having constant pressure inbuilt in them. So what this means is sigma I equals 1 to n ni double prime, open up the curly brackets and then say delta hf naught t ref plus hf naught at t add, okay, and hf naught t ref all for species mi equal to sigma I equals 1 to n delta hf. The right hand side remains the same as before, T1 HF, I'm sorry, yeah, okay, that's fine, T ref MI. Okay, now for a calorically perfect gas, of course, you can assume Cp as a constant and then you can explicitly, so now what happens is T add is showing up as what we want, it's actually a function of the sensible enthalpy, and so what you have to look for is, you now know, you can find out what the right hand side is. Okay, the right hand side is a known, you know ni single prime, and you know your T1, you can calculate these. So what you have to look for is if you knew your ni double prime, okay, ni double prime refers to the composition of the products given the composition of the reactants, and we will talk about that soon. Okay, if you're given ni double prime, you have to find out, so you now have to actually look at one particular temperature for which you could now look at the tables for the different species, okay, at that temperature and find out what this is and then see if it matches with the RHS, and then the temperature that you chose for looking at the tables for each and every species in the sensible enthalpy is right. If not, you start with a different temperature. So you can do this a bit iteratively, okay, or if you now assume a Cp as a function of temperature, you will now get polynomial in temperature and you have to solve this polynomial. So you will now get a temperature explicitly showing up as a polynomial which has to be solved for to get this temperature. If you want to get rid of all these hassles, and hopefully that's what you will face in things like exams, because you can do this very quickly, you assume a calorically perfect gas, which means you can simply say CPMI of T add minus T reference, and here you're going to have CPMI T1 minus T reference. So T Aerobatic is actually showing up linearly as opposed to a polynomial, okay, and then you can just rearrange and get your temperature, all right, okay. So that's easy for a calorically perfect gas, but not otherwise. So given Ni single prime and Ni double prime, one can find T adiabatic from the above equation, right, okay. So sensible enthalpy is also tabulated, as I said, tabulated in Janov tables as a function of temperature. These are now available on the web for typical species that you would be interested in, and so on. Okay, now I want to talk about two things here, okay, and these are the two most important things as far as this is concerned. So we now say this is equal to, here because QP is equal to 0, previously we had a negative sign and then the whole thing would be equal to QP, but now we have set QP is equal to 0, split this apart. So this refers to products, this refers to reactants, yeah. So we have to keep in mind we are thinking about combustion, and combustion is about burning fuels, okay, and we want to identify, but then the reaction that we took was something very algebraically general, okay, something like sigma I equals 1 to capital N Ni single prime script Mi gives sigma I equals 1 to capital M capital N Ni double prime script Mi. What was the fuel there? how is it getting oxidized? How do you know which is the fuel? How do you know which is the oxidizer? So we have this question, okay. So we wanted to be able to tell a fuel when you see it. How do you do this? What are we looking for when we burn? What happens when you burn a fuel? It releases heat. So how do you feel it? It's pretty hot, okay. So we are basically looking for a fairly high value of T adiabatic. Huh? What are the typical values of T adiabatic? Any idea? Or forget about T adiabatic. We don't even know whether you are having heat loss to the surroundings or not in the flames that you normally encounter, okay. But can you guess whatever is the temperature that you have in the flames that you encounter? Let's just take an example of the flame that you encounter. Example. Let's pick a flame that you encounter. Anything? I don't even know what the premix flame is. This is just a second class or third class. Huh? I want to talk about something that I encounter. Candle flame. So you now burn a candle. Okay. What do you think is the temperature there? Like the peak temperature anywhere inside the candle flame? Ballpark figure. Are we looking at a few degrees Celsius or tens of degrees of Celsius, hundreds of degrees of Celsius, thousands of degrees of Celsius, or 10,000s? I am going on a logarithmic scale. What are we talking about? Right? A few degrees Celsius is just barely more than ice. Obviously it's not that cold. Okay, a few tens of degrees is basically just barely more than body temperature or around body temperature, but when I touch it, it's pretty hot. Huh? So well, of course I can't touch anything more than about 70-80 degrees. I'm going to get burned. Okay, the human body is so fragile. Huh? You can't dip your finger into boiling water which is 100 degrees C. So we are not even talking about touching a flame. That means I guess the temperature is now getting greater than 100 degrees C, right. So is it hundreds or even worse, thousands? Thousands. So you light up a candle and you can get a temperature. Forget it, you don't even have to light up a candle. If you want to light up a candle, you have to strike a matchstick. You strike a matchstick, okay, and you get a little fire there. That flame is actually going to have a temperature that's of the order of 2000 Kelvin. 2000 to 3000. It's so hot, okay. But if you're into plasma physics and so on, it's only so hot. depends on what kind of person you are, okay. But we are talking about temperatures that are of the order of 2000 C, 2000 K. Doesn't matter when you're in 2000, whether it is C or K, okay, is a matter of the same order. Huh? Okay, so that's what we are looking at. If you want to get that high a temperature here, that means the sensible enthalpy has to be high. Okay, if your sensible enthalpy has to be high, the heat of formation here has to be low. That's the reason why we said a stoichiometric mixture is the one where the products will have the highest negative heats of formation. So now we are getting back to why we were talking about that. Okay, so we want to have products that have the highest negative values here, so that this will be high to compensate and get you the total. And then we have to look at the total. The total will be given by the right hand side. Okay. So the right hand side is already a given. You take a particular mixture of certain composition of methane and oxygen, let's say, okay, the right hand side is fixed at a particular pressure and temperature. You take everything, okay, temperature, pressure, composition, the species, everything, this right hand side is fixed. Then how do I know that I am actually working with a fuel and not some garbage? That means how do I know that methane is actually going to work like a fuel? That means I want to have a high total to begin with, that this gives you. The right hand side should be a fairly high total. and keep in mind T1 is not going to be very high for you. You don't want to actually heat up methane to 2000 Kelvin and then burn to get a carbon dioxide and water at 2000 Kelvin, doesn't make sense. So what is our methane at? Room temperature, okay, so room temperature is like, okay, 298 Kelvin, let's say. Okay, if you are now talking about a fairly low sensible enthalpy, how is it possible for us to now have a very high total of the sensible enthalpy and the heat of formation together? Only if you have very high heat of formation for the reactant. Okay, now if you have methane and oxygen, oxygen is not going to contribute to your standard heat of formation at all, because it's a reference element, and then therefore we take it as 0. Okay, so the only way you are going to make sure that your T adiabatic is high is if you worked with a particular species which gave you a very high standard heat of formation. So you now look at a species and find that it has a high standard heat of formation, you know it's a fuel. You see, that's really the catch. You get that and then you can burn and you can get very high temperatures, and that's the equation that tells you how to do this, right. So this pretty much contains like a lot of information about combustion, you see, very, very interesting. Okay, the second question that I have is, I can give you Ni single prime, all right, do I know Ni double prime? What is that? It means if I took a certain composition of reactants, how do I know what would be the composition of the products? Is it straightforward? See you Thursday.